Hey there, my name is Alejandro, and welcome back for day 224 of me doing the Daily LeetCode challenge that I reached 1 year's worth of great contributions here on GitHub. So today's one was for February 25th, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode medium problem 1524, number of subarrays with odd sum. Given an array of integers r, return the number of subarrays with an odd sum. Since the answer can be very large, return it modulo 10 to the 9 plus 7. Okay, first thing first, we'll do, okay, this will be 10 to the power of 9 plus 7. Okay. Okay, given an array of integers r, return the number of subarrays with an odd sum. Okay, can we do... okay, so we can't do n squared. Okay, otherwise what we could do is just prefix sum, so that way we can compute the sum of any subarray in O of one time. There's O of n squared subarrays. Okay, we have to do this in linear time. That's going to be interesting. Okay. If you can't iterate over every single index ij, right? Okay, so the very first thing that we can do things is this, right? Here we'll do prefix sums is equal to this. Cur sum equals 0 for num in r. Cur sum plus or equal to num. Prefix sums dot append num, right? And here we'll return, like, you know, sum of prefix sums of I of j minus prefix sums of I greater than 0 else 0. This modulo 2 equals 1. I in range for length of array for j in range plus 1 length of array. Right, something like this. Maybe this. Not quite. Okay, here we'll just do res is equals 0 for I in range. Here we'll just say n is equal to length of r. I in range n. J in range I plus 1 comma n. We'll do res plus is equal to those prefix sums of I minus 1 if I greater than 0. 0. Sums of j minus prefix I. And if this modulo 2 equals 1. Return res modulo mod. Something like this. Really, this is not working. Why is this? This should be working just fine. Oh, do I just need to do from index I as well? Okay, that fixed some things. 3 now. Zero, 0. I will get the whole end, right? Not quite. We'll just do print f string prefix sums from I minus 1 all the way up to j plus 1 equals. I just want to print out every single subarray that we're considering. We'll do it this way. Okay. Empty, empty. We're doing 5, 1, 3, 1, 3, 5, 3, 5. 3, 5, 1, 3. We're not doing 1. We're not doing just 3, and we're not doing just 5. I see. This is weird. So if I want every single subarray, it would be for I in range n, range I plus 1 comma n. Yeah, we want prefix sums of j minus I. Why am I having a hard time here? Prefix sums. I greater than 0. What? There should be 1, 2, 3, 4, 5, 6 subarrays. 1, 2, 3, 4, 5, 6. Okay. Subarray sum equals this. Is odd is equal to subarray sum. We'll say and 1 equals 1 if not modulo. We'll say res equals 0. Res plus or equal to is odd. Turn res modulo mod. Why is it not working? Subarray I equals j equals prefix sums from the j sum equals it's odd, right? Odd sum. What is this now? Like, all I'm trying to do is the brute force solution before I try to get to something linear. True, 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 false, false, false. 1 is true, 1, 3 is true, 1, 3, 5 is true, just 3. I see, so this is the problem. 1 and 1. Okay, first of all, oh my gosh, we're not doing curse sum here. Okay, well that might fix things. Yeah, okay, we were appending num instead of curse sum. Oh my gosh. Okay, because I was going like, what the heck is wrong here and so on. Okay, but yeah, here we can do return a sum of I in range n, j in range I plus 1, comma n. Here we'll say prefix sums of I greater than 0, else 0. Prefix sums of j minus this. And we'll take all this, end it with 1. Really? Or modulo 2. There we go. Really? What? Right? Okay. What is going on? Okay, here we'll say minus prefix sums of I minus 1, 0 else 0, and this here we do this and 1, range n for j in range I comma n. What? Okay, I don't get it. We'll just make things simple. Res equals 0 for I in range, and for j, oh, there's some weird indentation stuff going on. Okay. Okay, return sum, prefix sums. Okay, prefix sums of I greater than 0, else 0 for I in range n. So of j minus this for j in range I comma n. Parentheses this, and parentheses this. And now, and 1. Okay, we've made progress. Now, why is this wrong? Oh boy, we had just made such good progress. Of I minus 1, there we go. Really? Oh, now this is back to not being cur sum. Oh my gosh. We control Z too many things. Okay, now things are working. Okay. This is just way too much debugging for like too much ado for little nothing, right? Or however the saying goes. Okay. Let's just submit this. I expect this to TLE anyways. Well, this should just write the brute force solution. Wow, I'm getting slower with the LeetCode here. Jeez, okay. All I wanted to do was prove a point that, like, okay, we can just brute force our way and square through this thing, yeah, but we're gonna TLE and so on. Okay, this was just like, just to say, okay, here we're gonna TLE and so on, but like, we can essentially get the sum of any subarray in O of one time using prefix sums, right? Compute prefix sums, be able to obtain sum of any subarray in R O of one time. Here we can do lambda get subarray sum this will be prefix sums of j minus prefix sums of I minus 1, I greater than 0, else 0. So here we can just do get subarray sum of I comma j is odd subarray equals lambda subarray sum I comma j and 1. So we can just do this. Nice. And okay, so now this is what TLEs. Okay, sweet. But now we can essentially, like, we can say this is O of one time. This is O of one time, right? So we can use this as helpers, if anything. There we go. Okay, okay. Yeah, this is O of n squared, which is no bueno because here the input size is 10 to the 5, which means we're going to have to do something in O of n time. Although I see here, okay, R of I being up to 100 is very, very suspicious, right? That is indeed very, very suspicious. Okay, I won't think too hard about that. Okay, so one thing is... Oh, one thing that's nice about parity, right, is... Although, is it still not going to be O of n squared? Okay, because if I say, like, okay, if I know every single subarray sum from index I, ooh, then from index I minus 1, if I know, okay, that's actually going to be a cool idea. Suppose I know but these are subarrays, not necessarily subsequences, right? I was starting to think inside of DP mode. This might not be a DP problem, right? Yeah, this is subarrays, not subsequences. Okay. I was gonna say, if you know from index I plus 1 onwards that there are, like, say n or k subarrays, then you know that if your index I is even, then there are still, well, k plus 1 subarrays from that point on, right? If it's odd, then yeah, too bad, so sad. Right, now the only problem is if it keeps alternating, then that's a big problem. Ooh, I guess you could do, if it's opposite parity, then you could add that one until you get to a parity you do know. Okay, maybe this is DP. Right? Okay. Let me cook here. If I do DP, so, and then index I, odd subarray, odd subarray. Turn self.dp. Yeah, so here we'll just put a cache decorator, self.dp of I, range n. We'll do if I equals length of self.r minus 1, we'll return There we go. By the way, when I do and 1, this is the same thing as doing like, modulo 2 and if that's equal to 1, because like if it's odd, the very last bit of the binary representation of that number will be 1. If not, then it'll be 0, right? But you could just do like, modulo 2 and so on. That'll also return 1 and so on. It's just, I was like, I saw this once on a YouTube short and I was like, oh, that's a cool way of just checking the parity of a number. So that's why I'm doing it that way. Doesn't really matter at the end of the day. Let me think. If the number is even, self.r of I modulo 2 equals 0, then return self.dp of I plus 1. Otherwise, if we're odd, well, it's 1 for the current subarray. Is it going to be one of those where it's like a keep track of like the number of even subarrays and the number of odd subarrays? Returns num-odd subarrays, right? It's kind of like Eric Domain that one time where it was like, what is it? I think it was one of the LeetCode 150 problems where it was like product do the let me look over here instead of the LeetCode 150. Oh, it might not signed in. Let me just refresh. There we go. I think it was one of the DP problems here. I think it's maximum product subarray, right? Yeah, keep track of like, the minimum and maximum at every single point, because both of them might be useful for the next one, right? So this actually could be something like DP, where here I do num even subarrays. And that way it's like, okay, so obviously it's like, if the number is even, it's very trivial, right? Because it's just going to be like, oh, my number, for every single subarray from index I plus 1, I can add the number at index I because it'll keep the number odd, right? Adding an even number to an odd number will keep it odd. Now, if I keep track of the number of even subarrays and I add my odd number, all of a sudden, all those even subarrays, I make them odd, right? So if I keep track of the number of odd subarrays and number of even subarrays, that is perfect, right? Okay, just to be clear. There we go. So 1 if it's odd, and 0 if it's odd, or 0 and 1 if it's even. Okay, cool. Num even or num odd. Now this is easier if I do even and odd. I can do odd and even. Actually, let's do even and then odd. Sorry, I'm just my OCD right now. This is even. This is odd. Even, comma odd. 0, comma 1. So this will be like, number of odd. I is equal to length of self.array minus 1. cool. Num of odd, num of even is going to be equal to self.dp at index I plus 1, except now this will be, whoops, now this will be the num even. This will be the num odd. And so this is obviously our base case. We have a cache. This is perfect. Yeah, so here, if self.array modulo 2 is equal to 0, return is it just going to be num even, num odd? Because it's like, yeah, the number of even subarrays stays the same, the number of odd subarrays stays the same, because adding an even does nothing. Otherwise, what will we return? It'll be, should I add anything here? Oh, yeah. Here, the number, yeah. So here it won't affect anything because you're adding an even number. Now, if you have an odd number, since we have an odd number, just by itself, it forms a length 1 odd subarray. So num odd, we're going to plus or equal to 1. So that's how this is going to increase. Oh, and this is the same thing true here. Even subarray. So this will be num even plus 1 and num odd. Now this, what I'm saying is like, this will probably be num odd plus 1 num even, right? So now if we have an odd number, adding it to any even subarray will make it odd, and adding it to any odd subarray will make it even. So we swap the two values, but of course we increase odd subarrays by 1 as well for the singular element. And so that way we could do something as an even simpler base case. We could just do, if I greater or equal to length of self.r, just return 0, 0. There we go. Something like this might work. Not quite. RIP. For I in range n, print f string dp of I equals self.dp at index I. Of odd. Oh, wait. This should it be here? Because this is the number of odd ones, and here we're adding 1. Aha! Okay, we have cracked the code. Okay. Let's submit. Wrong answer, really. And at 148 out of 1. Oh, we're not, let's do modulo mod. Let's add that test case. Does that work now? Okay, beauty. And there we go. Completion streak 224 days. Consistency is key. See ya tomorrow. Okay, nice. Okay, hell yeah. It uses the exact pattern I was talking about. Oh, not here. Where is it? Maximum product subarray. This one, right? Yeah. It uses this. Okay, I wasn't using this as a hint to how to solve the problem, but I recognize like, okay, what if we did the same thing as in this problem? And so, okay, That's pretty nice. Eric Dermain do be coming in clutch from time to time. Okay. Sorry, here we can do something. So for example, if I in self.memo, return self.memo of I, and here we'll say, yeah. Here we'll just comment this out. Memo of I is equal to this else this. Return self.memo of I. We'll say res equal this, return res. Self.memo of I equals res. Here we'll do self.dp dot memo equal to an empty hash map. And there you go. Does that make things faster? Okay, considerably so, and so on. Although we still have a slower solution. Oh, is it because we just don't need this at the beginning anymore? Well, yeah, that would not be defined anymore. Okay. Well, that could be it. That could be a little bit of the reason why. Although not too much, not too much. Okay. If anything, we could bring this in locally. There we go. Cool. And here we can just do res equals 0 n res plus or equal to dp of I turn res modulo mod. Memo, come memo, R will be R. Okay, this will become DP. Nice. Okay. Memo of I equals this. Turn memo of I. This, otherwise this. Okay, I'm trying to figure out how to do this the best way possible. I see, maybe it's just I am creating a lot of memory. Base case, there we go. End of subarray. Implies some subarrays. There we go. I see. Okay. Maybe there's a faster way of doing this. I don't know. It's just I thought of doing this in terms of DP. Maybe the expected solution for this was not to do this in DP. So yeah. Then form length 1 even subarray will remain even including I, and similarly for all odd subarrays. Number is odd, then it will form a length 1 odd subarray, and all odd and all even subarrays from index I plus 1 onwards will now become odd subarrays after including number at index I and similar subarrays become even subarrays. So here we'll just do of I modulo 1, then otherwise equals this terminal of I, and there we go. Maybe now that's a little bit more readable. Index 1 is for odd sum counts. There we go. Okay, that's a lot better. We have the mod. Get number of even and odd subarrays, index I plus 1 onwards, cursively, num even, num odd, dp of I plus 1. And there we go. Okay, so still seemingly we seem to have a slow solution, but like, you know, this is just how I think of solving it and so on. Maybe like, you know, this is O of n, right? Because this is O of 1, O of 1, O of 1, recursive subcalls do not count. O of 1, O of 1, right? This is O of n, which each call will be O of 1 and so on. This is O of 1, or log n bits or whatever it is. Yeah, so like this is O of n algorithm, right? So this is a linear runtime algorithm. It's just, I guess, like the O1 stuff might be a little bit slow. So yeah, because you probably can't do this in like log n or something crazy, right? So, I mean, maybe I'm wrong and so on, but I'd assume the best solution for this is probably linear. We have a linear runtime solution, so I don't want to beat myself too much about not having high MS runtime. So it is what it is. There we go. I guess maybe one way is we could do things. We could do things bottom up, right? So here we'll just do. Here we'll say def num subarrays. Let's see. Subarrays. Top down. Right, so we could easily just make this return self dot of subarrays top down. Right, and this would work. Right, so maybe we do this bottom up. Length of R, mod is equal to power of 10 comma 9 plus 7. And here we'll say, actually one thing, does this make things faster? Well, that would not be quite nice, obviously. Oh no, it doesn't, right? Not quite, yeah. I was trying to think, like, is it just some demo of one thing somewhere? Okay, not quite. But maybe we can make things bottom up, right? So here what we'll do is exactly that. Here dp is equal to 0, 0. For +1. Num odd, num even, dp, y +1. Here we'll say dp of I is equal to, okay, we'll do this if odd, else this. Here we'll say even, comma odd, 0, 1, dp of I of odd. It's modulo mod. Not quite, eh? Wait, what? Why? modulo mods. Not quite. Print string dp equals. Right, these are passed by value, right? Zero three zero two zero one zero zero. Okay, something is going on. Ah, I know exactly what's going on. Lol, I am a dumb guy. Return res modulo mod. It should be num even. Num odd. Nice, okay, so is this faster now? Okay, so at least with 158 ms, we can maybe make things even faster. 0,0 range n comma num odd. Actually, we'll say num even comma num odd is equal to 0, 0. And here we'll just say num even is equal to this. It's supposed to be equal to num odd. Res equals 0. Nice. And what happens if I submit that? Hey, there we go. Okay, now we're getting closer to the solutions. Okay, okay. Beautiful. Beautiful. You can do res, comma num even, comma num odd equals 0, 0, 0. I don't know if that makes things faster here. Yeah, not quite. So we'll just do res modulo mod. We don't even need this now. Top down dp, still O of n, right? Nice. And this is the only time. Nice, 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 nice. And here we could even just do modulo 2 and see if that makes things even faster. I guess not quite. I guess it does like the and one. It's like in basketball, right? Like and one. Yeah. Very nice. Or I guess it doesn't really matter. They're both very, very fast. Yeah, they're both very fast. Okay. Bottom up dp of one space. So here we'll just call it. Yeah, there we go. Okay. There we go. Nice. Okay, I'm happy about the solution. We can submit this one more time. Okay, and there we go. Bada bing, bada boom. 83 beats 44.62%. Maybe we get a little luckier on the next one. Not quite. Okay, so but we're around the standard deviation. So there we go. Bada bing, bada boom. Okay, so as always in all my videos, I do a quick recap if I was able to solve the problem. So for this one, essentially, what we want to do is count the number of odd sum subarrays, right? And the very trivial way, which I actually took 15 minutes to do this at the beginning just because I was brain farting a little bit, is to, if you don't know, if you compute the prefix sums of an array, what it allows you to do is you're able to look at the subarray sum of any subarray in constant time. So give me two indices I and j, and I can return to you the subarray sum between I and j in exactly O of 1 time, as long as you allow me O of n time at the beginning to set up the prefix sums array, right? It's a very powerful technique. Although in this problem, the input size r.length is 10 to the 5, which means that you must build like, a linear or n log n solution. You cannot write a quadratic solution. And obviously, like, even if I can look at the subarray sum in O of 1 time, which I can then mean I can look whether a sum is odd or even in O of 1 time, it would require me to look at like, O of n squared worth of pairs and check like, add 1 for each one if it's odd sum or not, blah, 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 right? So it's an O of n squared solution. We can't brute force our way through, right? The way that I ended up going about this is actually doing a dynamic programming algorithm, which feels kind of nice because, it's been a little while since I did something DP. So it's nice to be back on track a little bit with the DP world. So essentially what I did is, I wrote a bottom-up solution that is a little bit faster over here, but the way that I initially solved this over here is via an algorithm that's still O of n with DP, but top down just to make things a little bit easier, right? And essentially what I was just realizing is like, if I can't do I and j pairs, I might as well do some things that are index I, right? And it's like, how am I able to know, like, how many subarrays there are from index I onwards? Well, maybe I can use, like, the number of subarrays from index I plus 1 onwards and kind of do something there to essentially make it, recursive subproblems, right? And what I realized is like, if, let's say let's say that, nums from I plus 1 onwards has k subarrays. Let's say there are k subarrays of odd sum in nums that start at index I plus 1, right? Then we could say it's like, if nums of I is even, then we know there are still k subarrays of odd sum from index I onwards, right? So if, let's say, from index I plus 1 onwards, we know that there are k subarrays that start from that index and onwards that essentially have an odd sum. Then we know that if at index I, right, we have an even number, then we know that, for every single subarray from index I plus 1 onwards, we know if there's k that have an odd sum, we know that, adding an even number to any single sum will keep the number the same in terms of parity, right? So if I add an even number to an even number, it's still even. If I add an even number to an odd number, it's still odd, right? So whether I add, when I add an even number, whether the original number was odd or even, it will remain odd or even and so on. Adding an even number has no effect. So I know that if I add an even number, essentially it has no effect. So if I had k subarrays of odd sum from index I plus 1 onwards, then I know that if nums at index I is even, then I will still have k subarrays from index I onwards that are of odd sum, right? And so I was like, there's going to be a little bit of a recurrence relation here, right? Now the only tricky part is like, what if my current number is odd, right? And it's like, first of all, there's a length 1 subarray that is odd, right? Just my number at index I is odd, so that's an odd subarray. But then it's like, when I add an odd number, I'll make an even number odd and an odd number even. It's like I swap things around, right? So it's like, it's kind of like, I can't really just use that anymore, right? So then I was like, maybe I started like, going ahead in the array and started like, thinking like, what if I just keep adding numbers from index I onwards until I reach like some even parity where I can do the things recursively. I was like, worst case, that's still going to be O of n squared because you could get even, odd, even, odd, even, odd, even, odd, and got kind of screwed with that, right? And so I was like, can't really do much there. So what else can I do? And I realized like, wait a minute. If I have an odd number, right? Then let's say I had, O subarrays that are odd sum from index I plus 1 and E subarrays of even sum, right? Now here's the thing. If index I, the number that is odd, then we know that, like, okay, first of all, there will be one odd subarray with just the number itself, right? But when I add that number to every single subarray that has an odd sum, those will become even in sum. And when I add it to any subarray that is even in sum, those will become odd in sum, right? So I figured, like, what if we keep track of both the even and odd sum subarrays? And then we know that, like, if we have an even number, it kind of changes nothing. Although we'll have one more even subarray because, like, just the number itself is a subarray that is even. And whenever we have an odd number, we form one more odd subarray. But then with, like, from index I plus 1, we know if there's O odd sum subarrays and E even sum subarrays, we know that we'll swap the two, right? Now there will be, like, E odd subarrays and O even subarrays, right? Because adding an odd number to any odd sum will make it even, and adding an odd number to any even sum will make it odd, right? So we'll essentially swap the O and the E. But when we do so, we also have to remember that, like, hey, okay, since the number was odd, we also have one more odd subarray now, right? And same thing with the evens. In this case, we won't swap, like, the odd sums and the even sums because they'll still remain odd or even when we add the number that is even, but we'll now have one more even subarray. And the thing that kind of inspired this for me is essentially this problem over here. I recognize, like, I've already finished all the 1D dynamic programming problems on LeetCode. One of them is maximum product subarray, which was a problem that I learned via one of Professor Eric Dermain's MIT OpenCourseWare lectures on dynamic programming that are freely available on YouTube. And this is a very nice trick. Essentially, like, this is asking you the maximum product subarray. The thing that makes this problem difficult is that if you see here, the numbers can be negative. And since the numbers can be negative, it's like, you might multiply, like, you want the maximum product subarray, but you might end up multiplying by negative numbers, which means that your numbers are very small. But remember that two negatives make a positive, right? So maybe sometimes you want to multiply something by a negative 10, and because later on you can multiply by negative 5, and there you go, you just multiply the current number by 50, because negative 5 times negative 10 makes 50, right? So the trick to this problem was always keeping track of not only the max, but the min. And that way it's like, when you add a negative number, it's like, you might make the min one, like, huge now, and so on, and like, you keep track of this over and over and over in similar spirit. And I just this problem kind of reminded me of that, where now it's like, okay, instead of always keeping track of odd sums, subarrays, we'll keep track of the number of even subarrays as well, because that way whenever we have an odd number, we need to swap those values around, and, like, they help us get to the whole end goal, right? So essentially dpf at index I will return to me a tuple with the number of even subarrays from index I onwards and the number of odd subarrays from index I onwards, right? Here's just, like, very basic memoization. So I have a memo hash map. If I is already in memo, then return memo of I, so that way it's like, I don't do duplicate work. If I've already computed the solution from one index I will just remember in my cache, which is what makes this O of n. A very trivial base case is, okay, if the index I is greater or equal to the length of the array, then it's like, okay, from index I onwards, there's nothing, right? And we're at the end of the array. So how many odd subarrays are there? 0. And how many even subarrays are there? 0, right? Very, very easy. Otherwise, it's like, okay, since I is not, like, greater or equal to the length of the array, it's a valid index, we'll get the number of even and odd numbers from index I plus 1 onwards by recursively calling our dp function, right? And if it's already been existed, it'll just, like, look in the cache, otherwise it'll compute it and so on. But, worst case, we'll do O of n calls to dp that are not like O of 1 lookup caches, but even here the work is all O of 1, so there you go. Because, okay, when you cache, you can ignore, like, the recursive subcalls, because, again, they'll just be a hash map lookup, right? So yeah, so here we just recursively call for, okay, from dp of index I plus 1, let's get the number of even and odd subarrays from there, and then we'll say, okay, if the current number is odd, right, this is just a number, way of checking if the number is odd, that's like, okay, since the number is odd, right, the number of evens will now become the number of odds, right? The second number is the number of odds, the first number is the number of evens, right? So the number of evens will be whatever used to be the number of odds, right? Because whatever we used to have as the number of evens, when we add an odd number to each of those subarrays, they'll now all become even. So the number of even subarrays will what used to be the number of odd subarrays from index I plus 1 onwards. The number of odd subarrays will now be the number of even subarrays, and here I have a plus 1, since because the number is odd, it also forms a length 1 subarray that is technically of odd sum right at index I, right? And then we just return that cache result. Otherwise, if r of I and 1, if the number at index I was even, then it's like, okay, things remain the same, right? The number of even will remain intact, and the number of odd will remain intact and unchanged. The only thing is I add plus 1 to the number of even, because since we have an even number, it forms a length 1 even sum subarray, so we add 1 to the number of even subarrays, right? And then we just return memo of I. And then what do I do for my solution? Remember, dp of index I returns the number of even and odd subarrays as a tuple. So we're gonna do, okay, for every single index I from range n, we're gonna compute like, the number of even and odd subarrays from index I onwards by doing dp of I, and we'll do at index 1. That way we get the odd sum counts, right? Because we care about the number of odd subarrays only, right? And so odd sum subarrays. So for every single index I in range n, we'll do self dp of I at index 1 to get the odd sum subarrays starting from index I for every single index I, right? And then we return res modulo mod, because here it says return the answer modulo 10 to the 9 plus 7 in case it's very large, and in this case it's like, mod is equal to just 10 to the power 9 plus 7 as we had before, so we just modulo by that, right? And that's pretty much it in terms of how to solve the algorithm, right? Here I just have some code that essentially does the exact same thing, but it does so bottom up to make things more efficient, right? I still have n is equal to length of the array, mod is equal to the power of 10 to the 9. Here I have res num even num odd. But I recognize that, like, okay, since I only need, like, the dp at index I plus 1 for dp of I can just go through the whole way and just do everything all at once, right? So for I in range n, it's like, okay, initially num even and num odd are 0 and 0 to depict, like, the number of subarrays that are even and odd from index, n, which is invalid. But that way it's like, we keep updating, number of even and odd subarrays as we go, right? So it's like, if it's odd, then do this. If it's even, then do this, like just like before. And then we'll keep adding, like, the number of odd subarrays that we see at every single step. And we're just going to keep doing this over and over and over, and then return res modulo mod, right? So it's essentially applying the same concept from here, but doing it in a bottom-up way instead of a top-down dynamic programming approach, just to make, the O of 1 stuff a little bit faster and give us a little bit of a faster solution, right? So instead of being here and being 5%, we're closer to the standard deviation. And if we resubmit a couple times, I'm sure that we'll get, like, closer, better solutions. So at least we were getting around here, right? Maybe if I do modulo 2 here instead of and 1, like in basketball, okay, like, maybe I resubmit a couple times, but, like, maybe it'll make things faster, maybe it doesn't, so it is what it is, right? Yeah, I guess it makes me even slower for now for some reason. But before we were getting, like, 60 percentage and so on, so it's still O of 1 stuff, but, like, might as well write it bottom up if you can and stuff. But yeah, this is what I mean. So now we're at 57%, so but we're close to the standard deviation or whatever it is. So this is probably a likely expected solution right here, and it feels nice because I haven't had a dynamic programming problem in a while, and it's the very first time. So this is the only time I've ever had to apply this concept inside of this problem, and this is a problem that I didn't have to solve myself. Well, I solved it myself, but I was able to solve it because I've seen it in an Eric Domain lecture. So to have a problem that I didn't expect to use that pattern and actually be able to recognize that pattern definitely feels pretty good to solve on my own. And yeah, so hopefully that solution makes sense. The trick is, again, for every single index I, keeping track of the number of even and odd subarrays, and that way it's like, as you keep backtrack through indices in the array, it's like it's like, okay, for my index I, how many odd and even sum subarrays were there from index I plus 1 onwards, and then I can compute the number of even and odd sum subarrays from index I onwards, and of one time depending on whether the number at index I is odd or even, right? And you do that for every single index, always adding, like, the number of odd sums subarrays that you see, yada yada yada, for every single index, and there you go, you have a nice and efficient solution to compute the number of subarrays with odd sum inside of R. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any shape or form, I'd highly appreciate if you left a like or a comment, but otherwise, I'll catch you next one. So till then, ciao ciao, my friend. Bye bye.